Hey everyone, this is the Algebra 2 Pre-AP Unit 15 review. We're going to be working through 8 problems that deal with variation and then also graphing rational functions. So let's go ahead and get started. Number 1, when you stand on snow, the average pressure P in pounds per square inch that you exert on the snow varies inversely with the total area A in square inches of the soles of your footwear. Suppose the pressure is 0.43 pounds per square inch when you wear the snowshoes, with A equal to 400 square inches. Write the equation of variation. Okay, first of all, let's just set up the plain equation that we've got going on here. We know that the pressure P, remember we always put that first variable here, and we always put equals, the K goes right after it, varies inversely with the total area A. So anytime it's inversely, it goes underneath the K's, we'll have over A. So now we can use the complete scenario that they gave us with the 0.43 pound per square inch and the area, and we can plug that in. So if the pressure is 0.43, we don't know what K is, that variation, constant of variation, and the area is 400. Then to solve for K, we can multiply both sides by 400, and we'll get a value of K equal to 172. So for that equation of variation that we're looking for, you're just taking that K and putting it back into your plain equation. So you'll get P equals 172 over A. And that's number 1. Okay, number 2, an Olympic skier will perform at their best when they wear custom-fitted skis and boots. This occurs when the skier's weight W varies directly with the width W, which is in inches, of the ski, and inversely with the length L of the ski. If the optimal length of a ski is 64 inches, if its width is 5 inches, and the skier weighs 187.5 pounds, what would the optimal length be if the ski is 6 inches wide and the skier weighs 200 pounds? So first of all, let's just set up that plain equation. We know that the weight W varies, so you always find that word varies, back it up once, and that's your variable that goes first. So we have W equals, the K always goes right after the equal sign. It varies directly with the width. Anything that's directly or jointly goes next to the K. Anything that is inversely with, which is the L here, will go underneath the K. So you have over L. We're going to use that complete scenario. We have a length of 64. We don't know what K is yet. A width is 5. And we have a weight of 187.5. So we need to solve for K first. So if I multiply by 64, go over here, then I'll end up with 12,000. Multiply on 64 on both sides. So we have 12,000 equals 5K, and then to get K by itself, we'll divide both sides by 5. So we'll get K equals 2,400. But we're not done here. We need to take that K value, and then also the fact that we have a 6 inches of width and a weight of 200, and plug that back in to find the optimal length. So the skier weighs 200. We know that K is now 2,400. We know this width is 6 inches. So we need to find the length. So if I multiply that L over and then divide by 200, then I'll get the length is 72 inches. Let's keep going. Andrew just got a weekend job working at the Burger Hut at the top of the Four Peaks chairlift. They have been short-handed and he has been working overtime. His overtime pay, P, varies jointly with the number of hours he works, H, and his hourly rate, R. Andrew's pay is $70.88 when he works 8 hours at $8.86 per hour. Find his hourly rate if he works 12 hours and receives $159.48 in pay. So as always, if it gives you a complete scenario with all the variables filled in, we'll solve for that first. So I guess we should set up our equation of variation first, but we don't know K yet. So we have his overtime pay, P, so we have P equals, always put the K right after it. It varies jointly with the number of hours he works, H, and his hourly rate, R. So we're going to have times H and R. Directly and jointly always go next to the K. Alright, so we have $70.88, so 70.88 equals K. His number of hours worked was 8, and his rate was $8.86. So if we figure out what 8 times 886 is, and we divide that over, so $70.88, we'll end up with K equals 1. So then find his hourly rate if he works 12 hours and receives $159.48. So we have 159.48 equals 1, which is our K value now. Then we have times H, which we have 12 hours, and then times his rate R, and that's what we're solving for. So we need to take each side and divide it by 12. So we'll get 159 divided by 159.48 divided by 12, and we get 1329. Now on to graphing. So number 4 here we have f of x equals negative 2 over x plus 2 minus 3. So notice that we have this in that transformation form, and you can tell because there are no x's up here in the numerator and we've got things subtracted after our function. So first of all, the vertical asymptote will be whatever is next to the x, the opposite sign. We moved everything to the left 2, including our asymptote that started at 0. So now we have an asymptote at x equals negative 2. Our horizontal asymptote will involve that number that's just at the end over there. If there's nothing there, it's 0, but here we have a negative 3, so our horizontal asymptote is moved down to y equals negative 3. That tells us that the domain will be the set of all real numbers where x does not equal negative 2, and the range will be the set of all real numbers where y does not equal negative 3. So remember, whenever we graph these in class, we would first of all start by putting the asymptotes on to the graph. So we'd have x equals negative 2, so that's going down right here, and then y equals negative 3. Oh, that's too much. Let's just use a marker. Okay, and then we can pretend like this new point right here is our new origin, this intersection. So we don't have to worry about moving left or right anymore. We can just look at the stretching part or the reflection part. So we had a parent point. Remember, the parent points are the 1/4, 4, 1/2, 2, 1, 1, 2 1/2, and 4 1/4. So if I just look at the y values and multiply each of those by negative 2, so if I was at 1, 1, I'll now be at 1, negative 2. If I was at 2, 1/2, I'll now be at 2, negative 1. If I was at 1, 2, 3, 4, 1/4, I'll now be at 4, negative 1/2. When I was at 1/2, 2, I'll now be at 1/2, negative 1, 2, 3, 4. And then I was at 1/4, 1, 2, 3, 4. So I'll now be at 1/4, negative 1, 2, 3, 4, 5, 6, 7. Oh, it'll be just off the graph, negative 8. So there's one side. And then the other side, we were at negative 1, so we'll be at negative 1, 1. And then we'll be at 1/2, positive 1, 2, 3, 4. 1/4, positive 5, 6, 7, 8. We'll be at negative 2. We were at negative 2, negative 1/2, so now we'll be at negative 2, 1. Oh, just noticed something. I didn't put it at 2. Let me fix that. When we were at negative 1, we'll now be at negative 1, 2. That looks better. I was wondering. All right. And so then we had negative 1, 2, 3, 4, negative 1/4, so now we're at positive 1/2. So there's the other side of our graph. All right. So let's check out number 5 here. We've got f of x equals x squared minus 3x plus 2 over x squared minus x. Whenever you're looking at these quotient of polynomials, it's always a good idea to factor them. And so this up here would factor into x minus 2 times x minus 1. But my denominator factors as well, and this was something that a lot of you would miss on, I think it was number 12 or 13 on your page 597. Please pay attention that if your denominator factors, which here this is x times x minus 1, ignoring that numerator for just a moment, that denominator, say nothing, it canceled here. That would tell us we had two vertical asymptotes. One would be at 0 and the other one would be at 1. So if your denominator factors, there's a possibility that you have two vertical asymptotes. But in this case, whenever we factored everything, the x minus 1s, they're the same thing, so we cancel those out. So now our function is x minus 2 over x. But we will have a hole in the graph since we canceled something out. So we'll have a hole in the graph at, so we take the thing that cancels, set it equal to 0, and solve for x. In this case, we'll get an x value of 1. To get the y value, you plug it back into your new function. So 1 minus 2, so we get negative 1 over 1, so that would be negative 1. So we're going to have a new graph of x minus 2 over x with a hole in the graph at at 1, negative 1. Alright, so writing down this information about this vertical asymptote here, we look at our denominator, and we look at when that would equal 0. So that would be at x equals 0 would make that denominator of x equal to 0. Horizontal asymptote, that's the Bobo-Botnide thing. If you don't remember that, make sure you go back to the previous video and check it out. But here they have an equal exponent of 1, so when that happens, you divide the leading coefficients. The leading coefficients here, we have a 1x and we've got a 1x. So 1 divided by 1, we'll get a y equals, yes, y equals 1. Okay, there is no slant asymptote since the degrees were equal, so we don't have to worry about that. For the zeros, you take the numerator, solve it for x. So here, I would get a 0 of 2, 0. Let's pretend for a moment that nothing had canceled. You would need to look at both of the things that were in the numerator to figure out the zeros. Okay? Alright, and then the y-intercept, that's when you're going to plug in 0 for x, so I'd have 0 minus 2, so it'd be negative 2 over 0. So if I had 0 minus 2 over 0, that's dividing by 0 and that's undefined. So if that happens, then there are no y-intercepts. Let's get back to this domain and range in just a moment. Let's graph what we have so far. We've got a vertical asymptote at x equals 0. We've got a horizontal asymptote at y equals 1. We do know that the 0 is at 1, 2, 0, so right there, and we don't have a y-intercept. So at this point, you need to start plugging in some values to calculate to find some other points. So if we plug in f, let's try f of negative 1. So we're plugging in negative 1 into that x minus 2 over x. So we'd have negative 1 minus 2 over negative 1. So that would equal 3. So you have the point negative 1, 3. And these x values that I'm choosing, they're just ones that are close to this vertical asymptote, and that's why I'm choosing those. Okay, let's try f of negative 2. So we'll have negative 2 minus 2 over negative 2. That will come out to equal 2. So we get the point negative 2, 2. And then we can pick one more on that side. Let's try f of negative 3. So we'll get negative 3 minus 2 over negative 3. So that would end up being 5/3, also known as 1 2/3. We have negative 1, 2, 3, 1 2/3. So whenever you have graphs like this, you can just pick 3 points on each side of the vertical asymptotes. Let's try on the other side. Oh, by the way, we knew there was a hole at 1, negative 1. So if we're looking at this, we know that there's going to be an open circle right here at 1, -1. So then let's pick one more point over here. We can say that the hole in the graph was one of the points. So then we'll try also f of 3. So we'll get 3 minus 2 over 3, and that's 1/3. So we have 1, 2, 3, and 1/3. So there's our graph. Okay. Number 6, x squared minus 25 over x minus 5. Again, always factor things to see if they cancel, which you'll probably be able to tell. They will here. So we have x plus 5 and x minus 5. The x minus 5's cancel. So now our function is x plus 5. But don't forget, there will be a hole in the graph at the x value will be positive 5 because we take the thing that canceled, set it equal to 0 and solve, so we'll get 5. To get the y value, plug that back into your new equation, so 5 plus 5, 10. So I have a hole in the graph at 5, 10. Vertical asymptotes. Now my denominator is just 1, so there's no x values there to worry about, so we have no vertical asymptotes. Horizontal asymptotes, again, it's no longer a rational expression, so I don't have to worry about that either. And of course I'll have no slant asymptotes because I don't have exponents to compare. The zeros for the graph, you take that numerator, that x plus 5, set it equal to 0 for your y value and solve, and you'll get x equals -5, so we'll have -5, 0. For a y-intercept, you're plugging in the x value equal to 0. So if x is 0, y is 5. So let's get back to this domain and range in just a moment and start plotting this. So all we have is a line at x plus 5, but we'll have a hole in the graph at 5, 10. So let's go ahead and put the hole in the graph. 1, 2, 3, 4, 5, up here at 10. Open circle there. And then we can plot the rest of the points. So we have a 0 at -5, 1, 2, 3, 4, 5. We've got a y-intercept at 0, 1, 2, 3, 4, 5. So then we would just need to draw in the graph. And there it is. Okay, just a couple more problems. We're almost done. But before we do, let's do this domain and range real quick. Okay, so the domain, it's just a line here, so it seems like it's all real numbers. So it's a set of all real numbers, except that x is not equal to 5 because there's a hole in the graph there. And the range is similar, so we have a set of all real numbers, but this time y cannot be equal to, we cannot have 10. So there's the domain and range. Now let's keep going. Number 7. F of x equals -1 over x squared minus 16. Again, I'm going to always factor if I can. So I have x minus 4 and x plus 4. So I've got two different things in my denominator here. So I've got two different vertical asymptotes as well. So I'll have one at +4 and one at -4. For the horizontal asymptote, whenever the exponent is bigger on the bottom, remember that's the bobo-botanide, B-O-B 0, so that'll be y equals 0. Because my exponent on top is really x to the 0 power, right? Anything to the 0 power is 1. If x isn't there, it's got an exponent of 0. So the exponent on the bottom is bigger. All right, and then slant asymptote, we don't have one. We had a horizontal asymptote. For the zeros, we have to look at when the numerator is equal to 0. We don't have any x's there to solve for, so we do not have any zeros either. For y-intercept, you plug in 0 for x, so we'll have that -1 over 0 squared minus 16. That's 1/16. So we'll have a y-intercept of 0, 1/16. And then we'll get back to the domain and range here in just a moment. But let's go ahead and start plotting the asymptotes. So we have two vertical asymptotes at positive and -4. So there's the negative 1, 2, 3, 4, and here's the positive 1, 2, 3, 4. The horizontal asymptote is at y equals 0. We know that the y-intercept is at 0, 1/16, so just right above it there. And we have 3 different sections we need to get a graph for. And so this is where we just have to start plugging in a whole bunch of things. So if we plug in f of, let's see, 1, 2, 3, 4, we'll go just to the left of this one, f of negative 5. We'll have negative 1 over 25 minus 16, so that's negative 1/9. So just right there. Let's get another one. If we do f of negative 6, so I have negative 1 over 36 minus 16. So I have negative 1/20th. Okay, so we're getting even closer that direction. So that means that our graph on this side is probably going to do something like this. For the part in the middle, let's try f of negative 1, 2. Let's try f of negative 2. So I have negative 1 over 4 minus 16. We get 1/12. So not very big there. If you plug in f of 2, because this is that negative 2 got squared up here, we'll also get 1/12. So it's just barely going up, but enough to know that we are going up on each of these sides here. And then finally on this other side, if we do f of 5 and f of 6, it should be the same values as the negative 5 and negative 6, since that negative number got squared. So we'll get negative 1/9, then we'll get negative 1/20th again. That's our graph. Just like that. All right, only one more problem to go. So here's number 8. X squared minus 3x minus 10 over x minus 2. Again, always factor it if you can. So we have x minus 5 times x plus 2. Nothing canceled. So the vertical asymptote, you look at the denominator, figure out when it equals 0. So that's x equals 2. For the horizontal asymptote, that's the Boba-Botnide thing. Here our exponent is bigger on top than it is on the bottom. So when it's bigger on top, there's no horizontal asymptote, but that's when you need to check for the slant asymptote. And you do that by doing synthetic division here. And we knew there was going to be a slant asymptote because 2 is exactly bigger than 1. The exponent in the numerator must be exactly 1 greater than the denominator. So our a value will be the opposite of this number right here, so we'll have a positive 2. We have a 1x squared minus 3x minus 10. Bring down the first term. Multiply and add. Multiply and add. Don't need the denominator. I'm sorry, remainder. And so this means we'll have y equals 1x minus 1, and that's the slant asymptote. Y equals x minus 1. For the zeros, you look at your numerator, figure out when that's equal to 0. So we'll have 2 of them here because it factored into 2 pieces. So we'll have 5, 0 and negative 2, 0. The y-intercept, you plug in the 0 for the x's and you solve. So we'll get negative 5 times 2 over negative 2. So then that ends up being 5. So we'll have a point at 0, 5. We'll get back to that domain and range. Which reminds me, did I ever do the domain and range on the previous problem? Probably not. I'll be sure to talk about it before we finish it up here. Okay. All right, so let's go ahead and plot the vertical and slant asymptote. So our vertical asymptote is at x equals 2. Our slant asymptote is at x minus 1, so it'll have a y-intercept of negative 1 and a slope of 1. Okay, so there's our slant asymptote, and then we will just start plugging in points. But first, let's see, did we figure out any? Yeah, we have 3 points here. We have the zeros 5, 0, and negative 2, 0. So there's negative 2, 0, and 1, 2, 3, 4, 5, 0. We also have our y-intercept is at 0, 1, 2, 3, 4, 5. So let's just get one more point for this left-hand side, so we'll have 3 points on each side. So if we plug in f of negative 3, we'll end up with negative 1 and 3/5 if you work that out. So then we'll have negative 1, 2, 3, negative 1 and 3/5, a little bit past there. So our graph will be kind of swooping up that way. And then for the other side, we'll need to plug in a couple of points. So we do f of 3. We'll end up with negative 10. So we have 1, 2, 3, and negative 10. So just right there at the bottom. And then how about one more? How about f of 6? We plug in a 6, so we have 6 minus 5 times 8 over 4, so we get 2. So f of 1, 2, 3, 4, 5, 6, up 1, 2. And there's the other side to our graph. By the way, I'm going to do this domain and range now, but it is really important that we go back and look at the domain and range from the previous problems, because I just forgot to do a bunch of them, didn't I? So sorry. Okay, so we'll just have a domain and range lesson real quick after this. All right, so the domain here is going to be, since we have that vertical asymptote at x equals 2, so that's going to be the set of all real numbers. Set of all real numbers where x is not equal to 2. And the range will be the set of all real numbers where, okay, so we have to be careful here. Do recall that whenever we had a slant asymptote, I said you didn't have to worry about finding the range, because you'd have to worry about local and local maximum minimums. But actually, as it turns out in this one, we will have all real numbers, but if you have a slant asymptote, you won't have to worry about the range. But this one does turn out to be all real numbers, because you'll see this would go this straight, but it would go down towards negative infinity, whereas on this other side it would go up towards positive infinity. So this one would be all real numbers. Okay, let's go back and look at the domain and range on the others. There's really a couple that I'm really wanting you to see. So let's go back. Here we are again, back at number 5. And I'm so sorry that I didn't do this before, but this is one that is especially important to talk about the domain and range. So looking at this domain here, we're going to have the set of all real numbers where x does not equal 0, as we're approaching that vertical asymptote, but we're not going to cross it. But we had a hole in the graph, so that means x can also not be equal to where that point is, and that x value was 1. So x will not be equal to 1 as well. For the range, it's a set of all real numbers where y does not equal 1, but also because of the hole in the graph, it will not be equal to negative 1 as well. So if you have a graph that has a hole in the graph, don't forget to include that hole as part of the domain and range where it cannot be equal to, because it is undefined at that point. So let's see if I missed any others. Sure did. Number 7. Okay, so the domain and range here. So the domain on this one would be the set of all real numbers where x is not equal to either one of these asymptotes. So x does not equal positive or negative 4. And then for the range, that will be the set of all real numbers where y does not equal 0. It doesn't cross the asymptote at this in this example. Remember, it'll only cross the asymptote if that asymptote occurs at one of your zeros. So there are the other two domain and ranges. I think we've covered it all at this point. If you have any questions, let me know, and I hope this was helpful. I'll see you later, and good luck studying. Bye.